in this seminar. I am very, very happy and pleased to be here. I see so many friendly and people that I met in other parts of my academic career. For instance, there is, well, Giuseppe and Alejandro, and hi, and also Mateo. Mateo, I think we met in a summer school or something like that. But yes, it's nice to see so familiar faces in the public today. So yes, so I am going to present you this ongoing work that I am trying to develop with my colleague Fabio Miranda at the Faculty of Science at UNAM. This is funded by two research projects at the university. So just to say that we are interested, or these research projects are interested, or they are focused in trying to close the gap between people in computer science or from the mathematical side, and also the people that are interested in some philosophical ideas related to computer-aided verification. So we are trying to have like a common background or a common playground in order to try to understand both sides of these important parts of epistemic stuff, and that also try to give the people like a common language in order to discuss the ideas. Sometimes we have the same interests from different sides from the computer side or the mathematical side and the philosophical side, but we never talk to each other. So this is hard to reconcile. So we are trying to make an effort, at least in the Faculty of Science and in the Faculty of Philosophy and the Institute of Philosophy Research. So let's start. I think I cannot. Okay, yes. So which language is the best to try to have both sides of both research sites in a common background? So we are using modal logic, a language that can be understood from both sides. Of course, we as a computer scientist, we have some specific usage of modal logic. And also from the philosophical side, there are other particular interests by using modal logic. We are working with traditional modal logic, let's say the classical modal logic, where we can talk about language, where we can try to represent this knowledge or sometimes beliefs about some set of agents. And we use, or we are really, or I hope you are also familiar with this notation, the box notation or the K notation, to represent or to say that something or some knowledge belongs or is known, or something is known by an agent A. And by an agent, sorry, and the thing that is known is the formula A. We are using also propositional logic, the propositional or the basic modal logic. And as you know, these logics are, or they have a very, they have a tradition of explaining and to interpret or giving interpretation of this operator, this box operator, in order to understand these ideas of knowledge. So they are well studied. So yes, they are sound and complete. They are usually they are presented with this style of axiomatic or Hilbert style proof systems. Also, you can or we can find in the literature some other systems, usually sequence systems, either natural deduction systems or sequence systems. But just for present the work here or the principal ideas, we will keep the axiomatic style of modal logics. So the modal logic for knowledge is the S5 system, and we have these schemes or these axioms. I don't like too much the word axiom because of my computer science background, but okay, let's say these axioms, they represent this idea of monotonicity in the knowledge transmission, let's say, the axiom or the scheme T. Also, we have the scheme or the axiom 4 that is previous or is, let's say, the basic also a scheme for modal logic. And then we have this extension of S4 with the axiom 5 in order to denotate some knowledge. As a Hilbert style system, we just have two inference rules. We can add other axioms. Indeed, we need the axioms of propositional logic in order to all these systems work together and try to make proofs. But we have just two inference rules, and we can have, or we can add as many schemes or as many axioms we need in order to represent knowledge. So this epistemic logic includes the primitive connectives, the knowledge and the belief connectives. And these two connectives, they are well behaved because we are in a classical setting. So this means that the diamond or the belief connective is a dual connective of the box or the K operator. And we can say that an agent believes something or believes a property or a formula. But also we can say that one formula or one information is consistent with the knowledge of an agent. And this is represented with the negation or the duality between these two operators. So this is very nice. We all are familiar with this. And this is the usual modal logic or framework for understanding knowledge and belief. But again, my computer science side ask a question and say, yes, okay, this is the classical setting. You can have these two operators to represent knowledge and belief. But what happens when you try to understand this modal logic in a constructive way or in an intuitionistic way? Why this is important, or why this we are interested as computer scientists as try to put our attention in these intuitionistic modal logics, because they are very useful to represent some computational notations, and in particular, its usage in distributed computing. So, for instance, we have, again, these two connectives, the box and the diamond, or the K and the B connectives or operators. But we can read them under another topic or in another area. We can say that if we have a code of type A, we can grab it or we can encapsulate it, and then we can talk about this encapsulated code and try to distribute it or distribute this code through a network. As the code is encapsulated, it is safe. We can say that we can propagate the code through the network, and then if if this code is in a particular computer or in a particular, I don't know, I don't want to use agent, but in a particular part of the network, it is safe to unbox this code and then execute this code. And the diamond operator is read or is interpreted as a creation or the management of resources, in particular the addresses. So we can read diamond A as the address or the address or the link of a remote value of type A. So with this interpretation, we can try to understand how the knowledge in our network is propagated and it's represented. And this is very interesting because from the earlier 2000s and I think before in the 90s, in the end of the last century, people started to work more and more in distributed computing because of the use of computers. So this intuitionistic model logic is also interesting because we can have, as I said, we can add as many axioms as we need in order to perform proofs. And these formulas, these model formulas, will represent types or specifications of the distributed computing in a network, in a given network. So, for instance, the axiom or the schema diamond 5 can be read as if we have an address of a mobile value A, then we can obtain such value. So this is really interesting, and this is also connected with epistemic logic and also some other areas of distributed computation. For instance, we have here another formula. We have box A implies B, and this implies diamond implies A implies diamond B. So yes, this is a long formula, but also this is interesting because we can read it under these distributed computing notions. And we can say that a functional mobile code, this is a process or a function that has input type A and output type B, can create an address in another part of our network for a function taking again as input a mobile code of type N and returning an address for storing or for the computation of the value of type B. So this is very interesting. This is mostly developed by Tom Murphy and other colleagues in 2004 and 2005 and 6. Also, there are other readings of intuitionistic model logic, mostly developed by Frank Fenning. I don't know if you are familiar with him, but he's very interested in trying to understand these models logics, also the LUCs modality and other operators, in order to understand these computational notions in distributed computing. So yes, we have intuitionistic model logic. What are the axioms and what is the setting of this proof system? What we have, as I said, many axioms. We keep the axiom. I think you cannot see my arrow here. Well, okay, doesn't matter.
Yes,
I will read it.
Yes, we can see your
okay.
Your mouse.
Yes. Yes, so we have the axiom K, then we have T, and then we have 5, and we are safe with the system S5. But as we are in an intuitionistic setup, the two connectives, the diamond and the box, are not interdefinable. So they are not the dual operators or dual connectives. So we need to add more axioms in order to keep all these notions and these representations of knowledge under diamond and K and box. We keep these two deductive rules, the modus ponens and the necessitation or the necessity rule, as you prefer. And also we can link these two versions of modal logic for knowledge, the intuitionistic and the classical one, by just adding the excluded middle axiom. So we are okay, we are safe. These two systems are related, and that's very nice. We can work either in the S5 system or in the intuitionistic system, and then we can relate the results from both systems. But our question or our main our main question is to understand what kind of epistemic logic is generated by ES5. We know that S5 is related with the epistemic logic and for understanding knowledge and belief, but the intuitionistic side remains quite not very understood or very studied. So again, I interested in these notions or these interpretations or these constructive interpretations following the Brouwen-Hating-Kolmogorov notions, where a proposition or a formula is true only if there is a proof of it. So in computer science and also in the foundations of programming languages and type systems, we are interested in representing specifications and types through the formulas of a given logical system or a system, and try to understand these the proofs of these formulas as programs. So yes, we just need to have the proof in our hands in order to understand what's happening in the demonstration of the specification, and therefore obtain or finally obtain a program from the proof. So the intuitionistic truth that I present by that we have in mind through the epistemic S5 system yields or give us the idea of verification and knowledge. So we are adding verification to the idea of knowledge. Box A represents that the proposition A is known, but also we want to have this idea of knowledge through the verification of a proof. So we need a basic intuitionistic logic of knowledge. We need a way to constructively talk about the truth of propositions and the proof of the demonstrations of some formulas. And also we need to have an acceptable formulation of these conditions, of truth conditions, and keep these ideas of that the verification, if we verify a proof, or if we can remake or check a proof of a proposition A, we can guarantee the knowledge of this proposition, of this specification, if we are trying to understand this under the computer science and the programming languages setting. So hopefully in 2016, Protopopescu, in his PhD thesis, discusses 3 ways of reading the intuitionistic epistemology by presenting an intuitionistic epistemic logic. The discussion in his PhD is, I found it like more philosophical in a philosophical way, without leaving aside these connections with the verification and the certification of information. So this is a well-established formalism for verified truth as knowledge, and considers knowledge as a product of verification. So we keep the axiom K, the distribution of knowledge. We have, again, modus ponens. We need to keep propositional axioms from the propositional logic, but we have different axioms to talk about knowledge. The first difference is that we have this correflection principle that is it's not opposite, but it's different from the axiom T. We also have intuitionistic reflection in order to represent that if proposition A is known, then we cannot say that A does not hold or holds. And finally, we cannot prove something false. So we have this consistent axiom that is the negation of the falsity or the bottom formula. So the key operator is read as both modalities. We can understand it or we can read it under the ideas of knowledge, of intuitionistic knowledge, because we are constructing the knowledge from a proof. And also we can understand, or we can read the K operator under the consistent intuitionistic beliefs. So we don't lose anything about knowledge and belief, but the system, this axiomatic system presented by Protopopescu, is quite different from the S5 system or the intuitionistic S5 system. Also in another article, Artemov and Protopopescu, they propose the reading of Ka as A is verified. But again, from the computer science side, a verification is not indeed a proof. So verification is the action to authenticate or corroborate something. So if I can show you a proof of a given proposition, you can read the proof and say, yes, okay, it's okay, I believe you. Or you can find an error or a gap in my proof and then just say, no, I cannot verify your proof. So we have this activity or this idea to reproduce the proof. And we cannot just read a proof if this proof is a long proof. Let's say sometimes we are not reading all the details in a proof. We cannot even sometimes reproduce some parts of the proof. And then also in computer science, when we cannot reproduce the whole program, we talk about certificates. So we can say that a program is or has a certificate that it works well, or it has a nice behavior, and it will have no errors. So a certificate, we can understand it as a witness or a guarantee that ensures that verification has been performed from a specification or for a program. And nowadays I don't know if you are also familiar with them, but we use many computational systems to support, to help, or to assist verifications. and also proofs. So these three words, or these three ideas, verification, certificates, and proofs, they are related, but we need to clarify when we are talking about one and another, and not try to use them indistinguishably. So what is computer-aided verification? We need to use a system, a computational system, to make proofs. That's my idea, to make proofs or just verify proofs. So if I perform a proof using one of these systems, I can just share with you a certificate of the proof, and not to share with you the whole proof or the many files that I develop or that I code in order to make a simple proof of something. There are many kinds or many levels of computer-aided verification. We have numerical verification just to make the arithmetical computations. We have model checkers, we have static analyzers, we have theorem provers, and the most sophisticated tools that we have for computer-aided verifications are the proof assistants, the interactive proof assistants. So all these systems always give us the certificates as the evidence or the validation of proofs. And also a certificate, we can understand it as a mathematical artifact that, again, gives me the guarantee that something has been verified or has been checked. It could be a proof, a long proof, a very complicated proof, or just a simple assertion. So we can use these systems in order to manage all the proofs. Here I need to make a comment, a remark, that we are not trying to understand how these computational systems are founded or are supported. We only trust on them. We can say that the people that develop these computational systems are very clever, and they have checked that the implementations and the fundamental theories of these systems are okay. So we are not trying to understand what happens inside these systems. We are just using the certificates these systems provide to the people. So for instance, we have many articles nowadays that in the conferences or in journals, they include this artifact or these certifications of the results or the verifications of the results in some work or in some contributions. So for instance, in this example, they use 3 different computer systems or computational systems in order to verify different levels of information or knowledge in this article. And this is very interesting because there are many assistants or proof assistant or computational system for verification, but they are not, they don't, well, they can work alone, but the interesting thing is that we can have these contributions between computational systems. As we collaborate as colleagues, we can try to work together. Also, the computer-aided systems or the computer systems to make proofs or to verify proofs can work together. So in this example, in this article, this certified verification of some properties of low level, blah, 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 they use different computational systems. They use just a system to verify some polynomial computations that this is hard for us as human beings to try to verify by hand. They also have some formalizations in the proof assistant. And finally, they use a satisfiability modulo theory solver in order to prove some satisfiability properties of the system. And they are using these systems in order to verify real cryptographic programs. But the main objective of these collaborations between these computational systems is to try to automatize the verification of the results. So they want to verify some properties of the programs with a minimal human intervention. So returning to the main question of what kind of epistemic logic is generated by the intuitionistic S5 logic or system, we have our proposal inspired from Protopopescu and Artemov intuitionistic epistemic logic to read the operator, the box operator, as that the formula or the specification A is certifiable. So I have any trusted software or any kind of this computer system, like a proof assistant or a SAT solver or a theorem prover. And this software may award a certificate for this proposition A or this specification A. Recall or remember that A is a formula, but this formula represents a specification of a computation or the specification of a program. So we have a certificate for this program by the modal operator box. And as we are in the intuitionistic setting, box and diamond are not dual operators, so we need to establish an interpretation for diamond A. And we say that A or the formula A is verifiable, and this is represented or read as there is a verification of A, maybe a partial verification. And the development of this verification involves some gap in some non-trusted software, or maybe we are using some admitted properties. So we have a partial verification, and we don't have a complete certificate for the formula A or for the type A. So again, there is a big discussion about certificates and verifications and all these notions. But we can think that a certificate is just the certainty that the property A or the formula A or the type A holds. But we do not necessarily have the proof at hand. I just have the certificate that gives me, or that is the output of using a computational system to perform something with the proof of A. And as if I remember well, Ricardo Blanco Martinez in his PhD thesis, he discusses also that sometimes an incomplete proof or an incorrect proof is not always without value. Sometimes if we have an incomplete proof or an incorrect proof, we can retrieve some information, or we can have or recover some knowledge from these proofs that are not complete or correct. So this reading of the epistemic logic, the box and the diamond operators, is interesting. I hope I can convince you that this is interesting from both sides. From the computer science side, because we are talking about the specifications of programs, and when we can talk about from or having a certificate of a type, and when we have gaps in these verifications. So under this reading or this proposal, we can, or we are okay, or we are respecting the ideas that were presented in the intuitionistic epistemic logic by Artemov and Protopopescu, and also the intuitionistic modal logic S5 where box and diamond are not dual operators. So as I mentioned, the intuitionistic epistemic logic has different axioms that the principal difference is this the axiom A implies box A or A implies KA, meaning that if the formula or the proposition A holds, then I can have a certification of it. And this is another reading of the intuitionistic epistemic logic given in the work of Protopopescu. And also, if we focus only in intuitionistic S5, we can see that the axiom T, box A implies A, can be read also as if A is certifiable, then I can be sure that A holds. And also, if A holds, then I can try to find a verification of A. Maybe an incomplete verification, but we can try to have a verification of A. Here I have different readings, different axioms under this reading of box as certifiable and diamond as verifiable. And I will not explain each of these axioms, but for instance, here we have the diamond bottom implies bottom. So we can say that a verified contradiction leads to a contradiction. So we are, again, having this kind of monotonicity in the knowledge. And for instance, the last one, I can say that if a specification or a type A or a formula A is verifiable, then this fact is certifiable. So we can try to wrap the idea of knowledge or having a certificate for a formula with this box operator, and it can be combined with the verification process in a very nice way. So again, we have here a logic or a language that can be used from the computer science side and the philosophical side. We both are interested in keeping this idea of having knowledge, but not just having the knowledge as I have a proof of a formula, but I need to ensure that I have a certificate for a formula, or I can have, or I can perform a verification of a formula. And this is also related because many mathematicians and also many philosophy people don't trust these computer systems, or they don't are interested in understand what's happening in a proof performed by a system of this kind. So we can try to see the certifications or the proofs developed in a computer-assisted system as a belief by an outsider. For instance, if I am not familiar with the Coq-proof assistant and someone shows me a complete proof of something in this system, I say, okay, you develop it and I believe you. I don't understand the language of the Coq-proof assistant, but okay, I believe that this is a proof and it's okay. And also I can consider it, the other people or the people that developed this proof in the Coq-proof assistant, he or she spends many hours proving something in the system, and for him or she, all the proof developed in the system is considered as a knowledge because he or she understands what's happening in each of the steps of the proofs. So I can say that again, under this reading of box A as A is certifiable and diamond A as A is verifiable, I can read this like, for instance, the K axiom as if I give a certified translation between assistants, for instance, A is a proof in an assistant, in the Coq proof assistant, and B is a proof in, I don't know, in a model checker or in a SAT solver, and I have a certificate between the translations of these two systems, then I can have, and if I have, sorry, an input, a certified input of the development in the Coq proof assistant, then I can have an output, a certified output in the other system. So we are trying to move on this combinations of these computational systems and have these intuitionistic or these epistemic readings as the common language between both sides. So, for instance, the last scheme or the last axiom says that a verification of a certificate of a given formula A indeed gives me that A is certifiable. So this means that I have the certificate of A grabbed under this box operator. And if I perform all the verification of this proof or develop or follow these steps in box A, at the very end, I will be sure, or I will have this knowledge that A indeed holds and also is certifiable. And for instance, another example, this axiom, A implies box diamond A, can be read as if A holds, then we can certify a verification of A. What's the importance or the importance of this? Imagine that you have a paper and pencil verification. You spend hours and hours trying to perform a proof by hand, and then someone is interested in your proof, and he or she tries to mechanize it in a proof assistant or in a computational system that helps verifying proofs. And at the end, this person gives you a certificate that the proof that you made by hand is indeed a correct proof, or that it's a complete proof because he shows you a certificate. So this is interesting from both sides. And the main question here is, okay, we have these epistemic readings of intuitionistic S5 system or logic, but how we can smooth the transition between both sides. Which sides? Well, the side from someone that doesn't believe in the computer-assisted proofs, and the side of an expert that uses these computer systems in order to perform proofs or to certify proofs. So we need to ensure that any proof becomes knowledge to the people that makes proofs by hand and the people that makes proofs using these computational systems. So a proof obtained by a formal verification process using these computational systems sometimes, as I mentioned, can be questioned as a true demonstration. Or sometimes they don't have the same purposes as a traditional proof. When I was presenting also earlier work of these topics, one philosopher told me, well, but the traditional way of performing proofs is like a human activity. Why you are trying to understand these computer-assisted proofs and trying to convince people that they don't use these computer systems, that indeed those proofs using the computer systems are comparable with the same way or the same activity or the same human activity that we use when we are trying to do a traditional proof by hand. So I think that this logic, this intuitionistic S5 under the epistemic reading, help us to understand that the verification process exhibits more or less the same phases or the same steps and applications when we are doing a purely mathematical proof or verification. And the correspondence between these two universes of traditional and computer-assisted proofs needs to be more closer. We need to close this gap within these two universes or these two worlds. So for this, we propose a definition of transitional proof in order to reconcile both sides. So I have a traditional paper and pencil proof of a given statement A. And also I have a valid proof script or a valid proof in the language of a proof assistant or in a computational system to perform proofs. And we can define this transitional proof with both proofs or the both parts of the both sides of this of the statement A. So the code or the script from the computer assisted proof need to employ different facilities in order to have the steps or the parts of the proof showed in a balanced way. And why we are taking this as a pair, why we take the traditional paper and pencil proof with the script under a programming system or in a computational system, because we need to parallelize both sides. So here we need a mapping. What you see is what you get mapping between those parts of the transitional proof in order to have a translation from the traditional proof and the code and the other way around, from the code to the traditional proof. And sometimes what you get is what you see is what you get. Mapping is not really easy to perform, because when you are working in a computational system that helps performing proofs, sometimes you need to internalize some notions of your proofs in what we represent as low-level operational tasks. So sometimes this transition between T and S is not clear enough, but this definition, this transitional definition, also help the people working in the computational systems to have a modularized way of defining the high-level ideas of the proofs that are indeed comparable to the traditional paper and pencil proof, and the low-level parts of a proof that will remain like I forgot the word in English, but these low-level tasks are not, let's say, public to the people that are reading this transitional proof. So they will keep in the low level, but we have these two sides. So how we can connect these ideas of closing the gap between traditional and computer-assisted proofs and this epistemic reading of intuitionistic S5 systems? Well, we can give an elaborated computer-assisted proof in the computer system that you like. Again, we can see it as something that can be trusted by someone that doesn't knows anything about this system, but is precious knowledge for the expert side of the proof assistant. So we can use this transitional proof, or this definition of transitional proof, in order to relate these ideas of having certificates and verifications. So for instance, if we have this axiom box A implies diamond A, we can say that if there is a certificate of the type or the proposition A, then we can ensure that A is verifiable. So again, we have these two, we can try, or we are trying to keep the best of both sides. And also we can expand these ideas, trying to represent different degrees of knowledge. So we can try to say that maybe I am an expert in the Coq proof system, but maybe, I don't know, other people are experts in the SAT solvers, or I have another colleague that she is only interested in performing proofs by hand. So I can represent the knowledge of this colleague from the traditional side, the other colleague that works in a SAT solver, and me that works in the Coq proof assistant, and try to represent the different expertise level of the three agents by adding this multimodal representation or extension of the epistemic logic in ES5. So this multimodal logic is a thing that we are working with Fabio, and we are trying to develop these Kripke models, or these Kripke foundations, in order to represent the different degrees of knowledge between different agents. So also we need to ensure that each agent has different capabilities. So we are also trying to incorporate the idea that each agent has its own language. Let's say that the language from a SAT solver is quite different from the language of the Coq proof assistants, for instance. And also, both languages are completely unknown to the agent that just works by hand performing proofs. So we need to recover these two levels. One is the degrees of knowledge, in order to explain this epistemic, or this idea of knowledge when we have a certificate. And also we need to incorporate another level in which we can talk about the capabilities that each agent has. So this is what we are working on. And I hope that this epistemic reading of the intuitionistic S5 logic is interesting for you, that maybe can help you also to understand different sides of the same things. And also that we in the future can have the same background or the same language, in order to compare our different degrees of knowledge and our different ways of communicating our results. Either if we are traditional agent and want to perform proofs by hand, or if we are a super expert agent trying to use the best proof assistant in order to perform proofs. Also, this idea of closing the gap between computer science and philosophy is always present in the discussions when epistemic interpretations came out. So these ideas of closing this gap are suggested not just by me or by Fabio, but there are other colleagues from the computer science side, mostly, that are interested in having a common language to discuss the same ideas in computer science and philosophy. And also, why not try to understand better our applications from the computational side that can help these epistemic logics in the philosophical side, and to enhance also our computer systems that we use to perform proofs. So this is the presentation. So thank you so much. And if you have questions, please open your microphone or just put it in the chat.